Okay, I think everyone is here. Benim var, buradan yapmıyorum. Today, I just wanna first say about it. If you have questions regarding to my previous lecture, you can ask about it like in 20 minutes, because this will be a little bit short presentation. It's due to the already commercialized, widely available technology. But I will get into details, how it works, what is the important facts for us, and what can you do about this technology. So we have single photons from several sources, as you can see, quantum dots, defect centers, heralding single photon sources which can generate single photons with an heralding mechanism, which means it's a photon pair source. You are just exploiting to use it as a single photon source. And if you remember, I just give you a little bit thinking homework regarding the what do you observe when you measure the one channel of the heralding single photon source. The answer is, I think already is mentioned in the previous lecture, it's a thermal state. You don't observe a single photon behavior, anti-bunching behavior, if you look at it. Why? It's in the math. Easily you can prove it. It has to be thermal state, otherwise it doesn't work. Anyway, so let's see, what do we have for the detection? How do we detect the single photons with some semiconductor or superconductor material? So you generate a single photon state, which means it doesn't come in bunches. You generate it one per time interval, so one by one, but you don't control the interval. It might be past, it might be little time difference between these quantum states or single photons, but you have to detect it. So we have cameras, everything, or single diode photodetectors for power meters in our laboratories or something like that. We use them daily, but how we can manipulate them to detect even single photon? How do they work? Let's check it. For example, you have a single silicon photodiode, and if it some single photon reaches that, you see this is like 100 micrometer or similar dimension square. And what happens? The photon is absorbed. There is electron and hole pair is created, but usually it gets lost. Why? Because you don't have the perfect semiconductor. There are some defects. Even the state of the art TCMC level, I mean the Intel level or etc. level semiconductor production, you will have losses. So you can't detect all the photons one by one. So what do? You use a engineering trick. You bias your diode in the metastable. I mean just above the, a little bit above the breakdown voltage. So it becomes so sensitive, even a single photon is absorbed, an electron will create an avalanche in your diode. And what using some electronics behind the detector, you can detect it now, which is called single photon avalanche photodiode technology, SPAD. So what is the properties? What is the properties we usually check for these? The external quantum efficiency, which means your device's quantum efficiency, or detection probability of single photon. Well, you are using silicon, so there will be absorption losses. There is a window over there to avoid reflection or protection of your circuit, and etc. So your external device efficiency never reaches 100% for this kind of devices. It usually depends on the wavelength or your device. It varies between the 5% to 60%. State of the art is produced in somewhere near Canada at the moment. It's like 75 detection probabilities available. So it's quite good. And And there is another good thing about this. You can easily implement in your integrated circuits without the electronics on the diodes. All right. Second is the time jitter. So time jitter means you are getting you are detecting photons one by one, but what kind of time you should attach this to these photons? The detection window or the detection jitter should be very small if you want to go to the high photon count rates or the fast gate operations, right? If you're detecting a photon like in 10 nanoseconds, which means then you are sending these photons to some kind of gate which can operate very fast. Doesn't matter. But if your detection rate is slow, then you will be limited to the several megahertz, which is very bad for a photonic computer. You are still trying to reach for a photonic or normal quantum computing to be operate in gigahertz or terahertz rates, which the quantum computing communities promised in the beginning in the 2000s. All right, and what we see here. Quantum efficiency, external quantum efficiency versus wavelength, or similar graph here, and we see the detection statistics of these photons from several photons together. So you have 40 picoseconds full fit-out maximum, which means your time jitter is about it. All right. Then since it's an avalanche photodiode. When you start an avalanche at the mountain, you need to stop it before you use it for another avalanche. So you need to quench the circuits with active or passive quenching circuits. Then it's what I showed you in the previous lecture. It's a little bit complicated device, but there is already two companies working regarding this in Turkey already, producing these modules. They are just getting the diodes from a very well-known semiconductor companies. Then they are producing these modules with you can just easily buy from the internet. Then you are getting a single photon detector. I will just give about the pricing range also, because you want to implement a physical structure, for example, in your lab. It depends. Actually, it begins from the 5,000 euros to 12 to 15,000 euros, even these devices. Because if you go to the very precise timing resolution and high quantum efficiency, then you will need the best of best diodes. And diodes, when they are produced in a wafer, they are produced like thousands together, and you pick only the good ones. So you are paying the price to pick the good ones from the production. And now the superconductor technology. Well, it was like I remember when first time I read about these articles, like I don't know, 15 years ago, I guess. Nobody think it will be a product today, which there are like 5 or 6 global companies can already sell you reasonable price. It's like 10 to 20 times expensive, more expensive, but for what it does, it doesn't matter. It's quite good. Okay, to understand this, we need to check how it works. So we have a narrow superconductor wires. Just put it together like this. It's under a little bit bias. Okay, when a photon absorption occurs here, you create a hotspot. It's just hotspot. You change the local temperature around it, and it will have a effect also in a neighboring region. So what happens? Your superconductor doesn't. What means it's not like ordinary diode or resistor. So it will create a little bit resistance. Okay. So with this configuration, you can just if it becomes this large, then you can just detect the current change or voltage change from this circuit. It's like a passive thermal detector. I don't want to say bolometer, but it's quite comparable technology. All right. So what happens? You observe the signal, and as you can see, there are a little bit noise because you are using electronics, etc., and you are using a superconductor, which is in low temperatures. And unfortunately, we don't have a room temperature superconductor like people claimed. Like, I don't know, last year, I guess there was a lot of debate about it, but it might get hotter, and there are already superconductors working on like more hot temperatures to even today. And the thing is, you need nanowires from superconductors. So you have to implement your fabrication process. And like this, the silicon photodiodes, it's like you produce several hundreds of them, and you only pick few of them because the distance between these superconducting wires and the dimensions of the superconducting wires determines which wavelength you can detect with this technology. All right, it doesn't detect all the wavelengths together, and this, even it seems like a bit a large spot size here, it's a very low or focused spot size. So it works only with work with the focused beams or optic beams or optic fibers output. And what happens? They usually sell it with already fiber connected modules. So you just send your signal to the optical fiber. It comes here to the all the way down to the cryostat, creates this hotspot, then you detect it. And this is the typical technological representation in the top right side. And how it began? It began in the 2001 SNSPD demonstration in the literature. Then since it was there was another quantum hype during this 2000, in the beginning of 2000, due to the quantum cryptography technologies. And there was also late the 2000, there was also already quantum project was conducting even here in TÜBİTAK in this campus. The SNSPD was a hot topic to be implemented technologically. So there was a lot of research. Now, one of the biggest companies is, I think, is Single Quantum, is just a startup company by a professor. Now it's selling globally, almost half of the market now. So you now, and even with this detector technology, you can apply all the region, or almost all the region of the visible and infrared, from the very narrow, like 600 nanometers to the 10 micron mid-infrared region, which is very good. So you don't need to work in some very well-defined region on photonic integrated circuits, which I will mention later. You have flexibility to work whatever you platform or whatever the wavelength region with this technology. But silicon is very limited to the visible range, actually the middle of the visible range. After 800 nanometers, the quantum efficiency of these diodes goes very bad. What do we have alternative also? I won't mention, but you have InGaAs, indium gallium arsenide technology. Germanium has recently caught a trend to about the research as a research topic, and but they produce very high dark counts. Let me talk a little bit about the dark counts. Since it's electronic device and even this SNSPD structures, they produce some noise, right? Every classical, and this when you measure the photons with this, for example, if you are measuring like 1,000 photons per second from your optical setups, depending of the quality of your device, you may have like 500 to 10 dark photons per second. So for example, you are using these detectors to measure some, photon anti-bunching behavior, right? If your signal to noise ratio or signal to dark photon ratio is very low, then you need to get a very large data set from your experiment. For example, you need to measure for a 1 hour, even longer time. But if you have a very bright source and your detectors are quite good, it will take just like few seconds to observe these things. Why this is important? You want to operate in a quantum computing environment to these devices. So if you wanted to operate as fast, then you need the highest detection ability with the lowest time jitter and with the lowest dark count. Then you can you will lose some of your photons due to this imperfection, but you can make fast calculation, and you may, in the end you can have a very fast working computer. And again, now this is the commercial product datasheets pictures. It operates now. You even order it with the cryostat control electronics. You just plug in cool the system. You plug in your optical fiber, and you just work it. It's that easy now. And this is the latest product from some company. It's like rack to put out on your laboratory. It's very quite enjoyable experiments now compared to the few years ago. What is the advantages of this technology compared to the silicon diode technology? It has very low time jitter. It can go like few picoseconds time jitter, which means you can operate in gigahertz region now for operations. It has very large, high quantum efficiency, like 90% for your working region. And it can easily already implanted some of the commercial products with your quantum photonic computer and the same chip, and you can cool down everything to the superconducting temperatures without damaging your photonic computer. All right, it has very low dark count, like 5 or 7 or 10 per second, and you can use them to create multi-pixel or camera-like structures easily. And one of the advantage of this I will mention about is you can create some photon number resolving detectors, not really photon resolving detectors, but quasi photon number resolving detectors, which is quite important. Because, for example, you are pumping an SPDC structure crystal. How do you know if you are getting the only single photon pairs or multiple photon pairs? You can use this system to detect that. And this is the state-of-the-art camera-like structure for a silicon photon technology. It's 500, approximately 500 to 500 pixel. It can go to the 100 kilo FPS per second, since it's camera. FPS means all the pixel rate in 100, I mean the kilohertz. It works in visible range, but you can go a higher rate than this. Then your resolution, timing resolution will be worse. And for SNSPD, for example, this is like implantation of photon number resolving detector. You have several inputs connected to the ones like you see some millimeter range devices. And for example, in the table we see that at the right side you see photon sands in the, for example, in this row 1 to the 8 photons you send, and how many of them you detect, how many, depending on how many detectors you use. So if you increase the number of states and increase number of the pixel, detection probability goes to the 10% even lower, but around the 3 to 4 detectors, it's actually quite good. 40 to 60% performance from you can get this device, and you can already order this kind of devices to produce for you from commercial companies, which is very good. Okay, now I talk a little bit side technology about this single photon detectors. What I mean by side technology, this single photon detectors produced a digital signal, actually, which we can see from this figure. It's like pulse. depends on your brand. It will be low voltage TTL, etc. Is a little bit rising behavior than falling behavior, but we can't easily make calculations on this behavior, right? So what we do generally, we convert this signal to some digital. I mean the time behavior, time tech, what we call. What I mean by this? When you detect a photon, for example, you have a circuit. When you detect this rising behavior from here, you just assign an integer for this rising behavior. And if you see another rising behavior, you send another integer for this, which now your time signal, digital signal is converted to time. Then you can do some correlations and calculate the G2 function, etc. Because if you remember, in the G2 figures, there was some delta T or tau product. You change it to calculate it. Okay. So from this behavior, you can calculate it. I will talk about it in detail in Friday about this. And if you are here around, you will be able to calculate G2 function in this here or in your home. I will provide you some experimental data to follow up later. And this is the one of the Turkish companies. It's not important, but in general, it's FPGA based device. There are some time to digital converters in there, and it can calculate GT functions for you on the when it runs easily. It can also produce lifetime measurement, and you can just, if you want the calculation by yourself with some code, MATLAB code, it doesn't matter. It can already calculate a transfer to a computer like a few hundred megabits per second transfer rate. But the state of the art is basically is the timing resolution, this low time jitter, etc. If you need the highest quality, highest technology available for your superconductor detectors, the price range then goes to like 40K euros. Okay, it's quite expensive timing device, and if you are making a very long measurement, you might have to do it, because if you want to sample some very complicated structures with multiple inputs and outputs, then you need to collect data on a longer time. Then you will time your timing resolution, or your timing, how can I call it? Your timing accuracy will be it will get worse. Because these devices have some very basic crystal structure for a clock to measure the clock. So you need to connect it some dependable atomic clock to get right measurements. So it gets complicated when you go to the quantum computing regime. Then it will add another 100,000 euros maybe to your optical setup. This was all about to detecting qubit states or DV states. Now the continuous variable states, I already mentioned a little bit, but in general, this is already well-established technology from the 70s, homodyne or heterodyne detection. Almost all the electronic engineers around the world learns this if they are working on the telecommunication sector, for example, or RF technology related things. Okay. So what we do for homodyne detection, there are two options. One is homodyne detection on the left. And for example, if you are not measuring two-mode squid states like you produced from same crystal, then you have one state, single state, or single mode behavior, Q mode behavior. You send it to beam splitter, and you send a very good local oscillator to this crystal, which I mean by its phase stability is quite good, has to be quite good. Power stability has to be quite good, and then you measure your signal output from the ordinary intensity detectors, not single photon detectors. But you measure the currents, but current difference. All right. not the current from the individual devices. Then from the current difference, which I will give more detail later during the Thursday talks, then you can get the phase intensity and phase information from this measurement, which means you can get the squeezing information from this, which means then you can learn if this state is squeezed or not. If it's a squeezed state, then you can use it, or you can implement it in a photonic quantum computer, or correlate it later for quantum operations, which two of the main driving research labs, one is Xanadu, other one is UTSC in China, Han Pei's group, is implementing this kind of technology, not the single photon counting. And for heterodyne, you measure everything, then analyze it together, but you won't be able to observe the quantum effects from this measurement. Is quite commonly used for other detects. So basically, this is some on-chip implemented device. We see some ring resonators and waveguides. It's four-way mixing device. Okay, it's a spontaneous four-way mixing device, but producing quantum modes instead of states. And you are using bandpass filters to filter it. Then you are using localist. This is two different Q mode. You can, as an equivalent of the DV states, you can see single photon sources like that, okay? Not photon pair source. So you send them to some beam splitter and you check the frequency response. What we do in laboratory usually, in laboratory, it's not easy to see the skew modes in the phase space. It's, yeah, you can construct this behavior, but what you see, if you look at the picture, we don't check this behavior in the laboratory, but what we check, the time dependence of the signal. For example, if you put the time axis in perpendicular to this x1 and x2, which is like propagating wire, okay, then you check this region, time dependency of this area, how does it behave. What you see, for example, some oscillating behavior with depending of time, like I said already, it's anti-squeeze state here, now skew state in the bottom, anti-squeeze state here, and squeeze state here in the bottom. And you see the shot noise. Shot noise is your fundamental limit with photon detecting event. You can try to reduce your shot noise by increasing your, for example, laser or your input power. What they do in LIGO, they use almost one of the most powerful lasers in the world to reduce the shot noise. But with this system, you can go below this shot noise. This is the quantum advantage of this system, and this is a quantum behavior. All right. For integration, SNSPD already implemented several devices, even for research and commercial companies. And here, what we see, some literature review here. We see some NBN structures from here already implanted with the silicon waveguide, which is produced together in a commercial foundry, and we see another multi SNSPD structures detectors together. Or what we see here, some nanowire on top of the some photonic circuitry, detector on top of your photonic integrated circuit, and you see the area is all like 10 microns, 20 microns. As a one dimension, and use with integrated device, you get the time jitter like to 20 to 100 picoseconds, and dark current rate is very low. Here we see, and operating temperatures depends on your structure. For example, this 300K is silicon, but the others are superconductor structures. It's very reasonable. 2K. For the 2K structures, you just need ordinary cryostat, continuous flow cryostat. You can just use ordinary purified helium to just use for the system. So you don't need dilution refrigerator for like superconductors to go to the millikelvin range. All right. So it's quite doable. If you want to buy this like system like Kroistat is like depends on the 30 to the complexity 30 to 100 kilo euros. It's not expensive. For a dilution refrigerator, you need approximately 700 euros in the beginning to start with. So and PIN diodes, which might be silicon in indium gallium arsenide or recently germanium. People started to work on germanium hybrid or silicon germanium devices, which is another hot topic to research now, because they're one of them recently, I didn't put here there, but they're very they observed very performance similar to the quantum efficiency of this superconducting detector. And they are already easily implantable with CMOS process to your silicon photonic circuit. And this is it for me today. And if you have any questions or from tomorrow or today.
In homodynamic detection, in order to understand the squeezing, like how much the state is squeezed, do you have to compare it with a coherent beam first?
Well, like I said, if you have two, this system produced single Q modes, single mode squeeze states, SMSS, what we call in the literature. Okay, and if you want to measure by itself, then you need a local oscillator. But what usually used by quantum and K distribution systems. All right, because you can implement some quantum information to those modes and use an information carrier. But for quantum computer, it has to be interact with other Q modes, because there are gates or even some interferometers already mentioned several times. So what we want, it has to interact with other modes. So what you for this measurement, you don't use a local oscillator. But what we see here, if you check, there is some phase shifter again. Because this the highest purity I will mention in Thursday, there will be little bit phase differences due to the material properties in atomic level, imperfections, etc. There will be little bit difference states produced from this integrated device. So you need to adjust one of them phases to according to see this behavior.
Orkun Hocam, may I ask a question from Zoom?
Yeah, sure.
You mentioned about the photodetectors that are being utilized in the single photon detection devices. Are any of these photodetectors, or are there any of them A3B5 type? Because I didn't hear that you mentioned those types, so I was wondering if there are any A3B5 single photon detectors.
A3? Well, I didn't understand.
The A3B5 type photodetectors,
You mean the periodic table group 3-5 detectors?
Yeah, yeah.
Yeah. Well, there are some like indium gallium arsenide, which you can easily call group 3-5 detectors. But like I said, the problem with these detectors, even for the defense applications, their dark count rates is quite high. For example, if you buy a single photon detector, which is based with the indium gallium arsenide technology, which is commonly used for infrared now, their dark count rate will be, I don't know, 10 times worse than the silicon, which 100 times worse than the superconductor detectors, which cannot be used for quantum computing at the moment.
I see. Okay, thank you for the information.
It makes them more efficient compared to silicon because of the
yeah, they are good for infrared, but the technology is lagging behind due to the silicon, because silicon CMOS technologies are dominating the world. So what we want to do for every new technology, implement everything into CMOS. What I mean by that is just wafer production or device production with chemical etches, deposition, etc. If it's compatible with the CMOS, you can easily order from a foundry and you can do research and start a company. Just designing. You don't need to discover the earth again for new technology. Like we are experiencing with the superconducting now.
I guess for SNSPD, we need a very stable environment in terms of thermal noise. So how do we ensure our detector is good completely enough? Environmental as in like temperature change.
In terms of mechanical vibration, this device is a passive device. It's just some waveguides implanted on some wafer, all right? So it's cooled down to the several kelvins, depends on but the most commercial products cool it to 2 kelvins or 4 kelvins, okay? It stays in vacuum also. So, and yes, you need a little bit mechanical stability, but it depends on your laboratory. If you are in a very noisy, as a mechanical vibration environment, you need to put it on some optical table with active damping, etc. Right? Yeah, but in general, they are quite effective. You can ever jump around them; they won't be able to affect from there. But for a electronic noise, yeah, it depends, but it's like Faraday cage, all metal closing around it. So yeah, and I forgot to mention one thing about these detectors. Since they use single mode fibers usually for if you remember from your electromagnetic theory lessons, I don't know how many you have reached the last fifth chapter of the Jackson's book, but when you solve the equations, you will see a cutoff region for single mode fibers. So you cannot use all the visible or infrared range. It will be few hundred nanometers range, like 150 nanometer. Depends on your optical fiber, the working range.
You mentioned that the hotspot in previous slide. Is it like a pressure trap point? How it can be controlled? Because the temperature diffusion.
Yeah, it's like it's a superconductor. It's in the superconducting state, but it might get to the normal state. It depends on your material. I mean, it can lose your superconductivity. So when happens, before just happens to that, you see some voltage spike due to the heating, local heating. So this is local heating. Your temperature of your device is a little bit changed. Yeah. But in general, I am not expert on this topic. This is quite sophisticated production and material science thing. Yeah. Yeah. Yeah, it depends. But this region is like, when we see like how many waveguides are here for, it's like 1 micron. Spot is like 1 micron, 1 or 1.5 microns, etc. That's it. So it's quite fast. And phonons, you know, when they repopulate, even at this low temperature, it's quite fast. It's if I recall correctly, should be 10 to the minus 15, 10 to the minus 15 timing range. Yeah, so it's very fast process compared to what we are trying to observe is in picosecond range.
I have a question. So I'm not sure if I understood correctly, but I think I heard you say to make a quantum computing system with MV centers in diamond. We need only the emissions from electronic state. And doesn't that mean the zero online? neutral state.
It depends on what kind of quantum computer you want to build. If it's a spin-based, if you are relying on the spin interactions, should be if you are relying on the spin interactions, that's different kind of the quantum computer. It's stationary qubit quantum computer. You can use gate-based technology easily, so spins will interact. You can use photon-related or emission or absorption-related effects to manipulate the spins, but you don't use the photons emitted from this technology. But if you are trying to use this as a single photon source for a photonic quantum computer, then it's a very bad idea. Because you need a very sharp line like this one in the 80 kelvins. Even this is a bad one. You won't be able to. Let me say this way. This is a very sharp line you see here in this region, right? And it's very similar to the Lorentzian or even Dirac delta. But for this moment, there are only two bad Hongo-Mandel visibility measurements for hexagonal boron nitride. Normally, we should be able to see it from the spectra. So because it's the phonons, this is now the acoustic phonons. We are very close to your emission range. They are making your emission is decoherent. So your coherency of your system between the different photons, it's get lost. Well, like I said, you cannot for even single photon because the phonon sideband, there is also the phonon sideband. I'm sorry. Phonon sideband is here. It's just hidden. Why this? I didn't show it because you see the phonon sideband here clearly. But also NV0 has a phonon sideband, which means you're losing your pure electronic state transitions to electron phonon related transitions.
Okay, thank you.
But this structure is quite good, already implanted, because we can produce the engineerly, which one of the quantum technology companies, Candela, it was a startup a few years ago. Now it's a very big company. I don't know, maybe several hundred workers on it now. You can get a very sharp line, which I can. You see. Sorry. This one in the right side, they are very sharp. And if you check the scale at the bottom, it's milli-electron volt range. It means it's very, very, very sharp. If it's very sharp, if it's not get broadened by the electron phonon interactions, then the phonons, it doesn't affect your system that much. You can use it. Maybe in theory they couldn't get very good result from the system yet. Because they are using phonon sideband, they are trying to stimulate the system from phonon sideband also. They are not using resonant. You have to be used resonant. You have to excite the system resonant. But this is another problem, like I mentioned before. You need to get rid of laser. But very recently, let me make some commercial here. One of our recent colleagues get his PhD, Yusuf Karlı in Innsbruck. Demonstrated you can use some other effects to excite the system. It's called super in short terms, which is quite good. Then you get rid of this effect. It's very hard to implement, but it's a start. Okay.
Are the peaks in the photoluminescence spectra from the NV center? Is it coming from a single NV center, or could there be like more than one?
In this spectra, it's more than one, but it will be similar to this. But why I'm strong is because all the spins emitting same spectra, it gets a little bit wider, but it's not that bad. But MV center or this kind of defect which has a strong electron phonon interaction influence on this system, it's not good idea to use them for in the applications require indistinguishability. But not all the applications require indistinguishability. I think we have time if you have any more questions. I don't know.
If you think about the continuous and discrete approaches, in the future, which one will be more popular, I would say?
Yeah. Well, that's a good question. I will get into detail in Thursday, more detail. I will get my glimpse of the future about the photonic quantum computer. But as a preview, there are two main approaches for photonic quantum computers. It's already mentioned, gate-based, doesn't work quite good for photons because they don't want to interact each other. They don't like to interact. So in perfect world, you need a perfect medium with a 100 efficiency to interact them. But as you saw already, nonlinear effects, it's the efficiency of these effects very low. So there is not too much going on as a commercial side on the programmable qubit-based systems. But on the other hand, if you look at the measurement-based systems, it's like you operate the system by measuring it. Gates are implanted on the measurement system, which is a quite good approach. There are also several drawbacks about it because you cannot use the simple single photon states anymore. In regard of the continuous variable systems, there is only one implantation now. It's the Gaussian boson sampling. I will get into detail that. It's a very good application. But recently, some people in one of these companies start to think about it. How if we can program these continuous variable photonic computer systems? What happens? Can we operate them like gate-based systems? Can we think about out of the box to implement new type of the quantum computing? So this is the hot topic now. If it happens, they already demonstrate several qubits on a tabletop systems operating very efficiently, solving problems. If you check the literature now, quantum advantage, real, I don't want to say these terms, but the real quantum advantages come from the boson samples now, the sampling now. Because it's a real problem. Sampling a distribution system is very hard, and these systems can make it calculate efficiently.
Is there any practical use of it?
Gaussian boson sampling? Well, a lot. I think tomorrow one of the lectures will mention about it. I will also mention about it on Thursday. But let's say there is some basic problems we want to solve, like some statistical distributions. What I mean that if you have like you are walking in a labyrinth, that's a very bad analogy, but okay. If you have lots of beam splitters on your path, like labyrinth, right? You have lots of, if you want to turn to right, turn to left, or go straight, you don't know. But you want to calculate what most probable solution for this system, which one works. And what standard computer, what does, it has to calculate every path, everything. And if you think about some differential equation, it might be an ordinary differential equation, then you can implement in some determinant, then it's a matrix problem with lots of variables, then you need to solve it. It's a very hard for quantum normal deterministic computer. Even with the like Earthshaker or something already built in the US, the matrix diagonalization or finding your eigenvalues or the required solution is very hard. But this kind of technology, it's very easy. You just need, I don't know, for ideal system, few seconds, or very bad system is like few hours. You can get the answer even without getting the labyrinth.
We are getting a sample, of a probability distribution. Right?
Yeah.
This, how does it relate to the actual eigenvalues and eigenvectors?
Well, it depends what you want to know. If you want to know every, for example, coefficients of these differential equations, then it's, yeah, you need to solve it by one. But if you just need one operator, can go which direction. Let me give some more detail expanded in my expertise of view in defense sector. Okay, you have an airspace. You are in Ukraine. You have an airspace and you are a ground state. You have lots of operators, animals, drones, marines, etc., and several country troops. All right. So, and you want to calculate what happens if one man tries to move one region to other region. Then this is the same problem, right? In lots of interacting particles, then you need a lot of qubits, of course, or Q modes for this system. But you want to calculate some probability, just this probability, not the whole system. But for a deterministic computer, you need to integrate all the variables to this system. But then just this probability, you can just manipulate the system to get this outcome or the probability of this. For example, if my man goes to turn this side, then go this side, then if you follow this some path predetermined, what is the probability of this? It can calculate easily. Like I said, but this is what I understand from these algorithms. I am not algorithm expert. I don't want to overstep my expertise.
Can I ask you about the last things you mentioned, actually? I mean, you mentioned that we can achieve some very cool things. Will you tell us these in this whole school? If not, can you give us a little introduction at least?
Well, I can just show you what I will talk about, a glimpse of what I will talk about. Let's start a little bit since we have some little time. I will talk about a little bit the general quantum computing, then the advantages, disadvantages, and like I said, what kind of alternatives we have. A little bit gates operation, but from an experimental perspective, not some algorithm or theoretical physics perspective. Then what do we have as a technology and what we need now? I just want to, what I am here, just give you some insight about the technology, and I want you to be the next person to deliver a newer or some kind of clever thinking to implement an algorithm to this system. Because this programmable Gaussian boson sampling, this start of this idea, they thought that there's a problem. Let me show this slide quickly. Yeah, they thought they wanted to, because in the left side we called Galton board. It's quite hard for a deterministic system, even for a very supercomputer. But analog computers, or like very basic analog computers, which is built around 2000 years ago with water flow, they can simulate the system easily. But why not the deterministic classical computer cannot do it? Because they work in a deterministic world, not the probabilistic world. All right. So if you check the Gaussian boson sampling, like it said, you implement some extra features so you can get the required results or results around your problem, not the whole picture. So I will talk about this in later and what's the problems, how we implement. It will be quite long day for Thursday for me. I think we have like 180 slides remaining. Okay.
Yeah, thanks.